Uh, Hi everyone. As Farooq said, my presentation today title is Alternative Difficulty Adjustment Algorithm for Preventing Selfish Mining Attacks. This is actually a combination of two of our recent works. That one of them is accepted at International Conference on Blockchain, and the other one is under review. So, as the title suggests, it's about the difficulty adjustment and mining process and the preventing selfish mining attacks. So this is the outline of my presentation. First, I will go into a very brief introduction, and then I'll define our problem here, and then I will propose our methods, and then show you analysis and results, and at the end, a conclusion. So I think all of you are familiar with Bitcoin. I'm starting with the Bitcoin mining process. Bitcoin mining is a process of generating new blocks and appending these new blocks to the blockchain. And for doing so, every miner should provide a proof of work. So it means that the hash of the block header, these blocks, essentially the blockchain is a chain of blocks, and these blocks has transaction as data inside them. So every miner should provide a proof of work, and it means the hash of the block header should start with a specified number of zeros. Because the hashing process is a one-way function, this is done by using a trial and error method. So they should choose different nonces, which is one of the contents of the block header, and then use different nonces to provide a proof of work. The proportion of blocks that are generated by a miner has a direct relation with the share of the hash power in the network. For example, let's say there is, so in the Bitcoin network, there is a lot of miners, and for example, let's say one of the miners has 20% of the hash power of all the network. So at the end, it should be it should generate around 20% of all the blocks in the network. So the number of blocks that a miner is generating is directly related to the hash power of the miner. Block generation and difficulty. Bitcoin tries to keep the generation rate constant. It means in the Bitcoin we want to have one block every 10 minutes. If we have more miners in the network, it means they can create a new block in less than 10 minutes. And if you have less miners, it means they can create one block in more than 10 minutes. So what they want to do is that make this block generation constant by increasing or decreasing the difficulty of the network based on the number of blocks that are generated in the previous period. So the number of leading zeros in the block header, hash of the block header, determines how difficult the mining process is. The difficulty value could be adjusted to achieve this desired block generation rate, which is 10 minutes or 6 blocks per hour. This process is called difficulty adjustment, and it happens every 2016 blocks or 2 weeks. What is selfish mining? Selfish mining, introduced by EL and Sears in 2013, is an attack to the miner, to other miners, from one miner to other miners. And this is a strategy which a miner or a pool of miners can use to obtain more revenue than their fair share. In the essence, it's very simple. Keep your discovered blocks private. It means if you keep your discovered blocks private, other miners do not have access to the latest block to mine on top of them, and they are actually mining on top of an old block. And so by doing so, the miners or the attackers intentionally fork the blockchain, and of course they will reveal it whenever needed. And by doing so, they can waste honest miners or honest nodes hash power. So it means if you are working on if you don't have access to the latest block because a selfish miner is not sharing it with you, you are are mining on top of an old block, and then your computational power is going to be wasted. This is the selfish mining. And in selfish mining, in their paper, EL and CR analyzed this this behavior and this selfish mining, and came up with this figure that you can see. And as you can see, this gray line here shows the fair share. It means if, for example, as I mentioned earlier, if one miner has 20% or 0.2 of the total hash power of the network, it should get 0.2 of the relative revenue of the network, or the number of blocks that it generated should be 0.2. The proportion of its mine block should be 0.2 also. But here, as you can see, in some cases, I can say in many cases, they said that EL and CR said that this selfish mining can obtain a revenue more than their fair share, so more than this gray line here. There is two parameters in their work, and one of them is alpha, which is pool size, as you can see on this x-axis, and the other one that you can see here is gamma, which is the number of, or the proportion of honest miners who choose to mine on the top of the selfish miners block. So the worst case for the miner, for a selfish miner, is when gamma is 0. It means none of the honest miners choose their block, and the best case is 1, is when all of the honest miners choose the attacker's block. What you can see in many cases, they show that this value, the relative pool revenue, is more than their fair share. This is the analysis that EL and CR did on their original book. But there is a debate between at one side is EL and CR, and the other side is Craig Wright, which is one of the most important people in the Bitcoin community. And there is a debate here, and EL and CR says that the selfish mining works in many cases, but Craig Wright says it never works, and it's actually a fallacy. So on the right side, you can see the figure from the previous slide on the left side, and on the right side, you can see analysis of Craig Wright in for the same thing. So as you can see here, they choose gamma equal to 0, same as the red line here, and they argued that the actual curve for a selfish miner is this one, this curve that you can see right here, and it's always below the gray line, not this line that they mentioned here. So who is right here? Which analysis is correct and which one is not? So we can say both sides of this argument failed to see or show the big picture here. And EL and CR's analysis show the final value of the revenue after many difficulty adjustment periods, while Craig Wright's analysis shows this before the difficulty adjustment in one period, in the first period actually. So we can say in the short term, Craig Wright is right and correct. Their analysis is correct, and in the long term, EL and CR's analysis is correct. And this is the profitability of selfish mining, the same figure that they showed in their work for before and after the difficulty adjustment. As you can see, for before the difficulty adjustment in the short period, all of these curves are below the gray line or black line here. It means selfish mining is never profitable. And on the right side, you can see it after many times, after many difficulty adjustment periods, and in this case, many of them are above this line. This is from our analysis, which shows both of them are correct in some ways, but not in like every scenario. So what is our problem here? As we talked before, profitability of selfish mining changed over time. It's at the beginning, before the difficulty adjustment, it is not profitable because these curves are, all of them are below this line, and after the difficulty adjustment, in many cases, is becoming profitable. So only after the difficulty adjustment, selfish mining starts to become profitable. So we can argue that the difficulty adjustment is the main reason that selfish mining becomes profitable, but we cannot remove it because we need the scalability. Because if we have more miners, we want the network to have the constant block generation rate of 10 minutes. But we can modify this algorithm, this difficulty algorithm, to reduce the effect of attacks like selfish mining. So this is our formulation for the evaluation. This is actually our evaluation metrics. The first one, our pool of T, is the total net revenue of the pool for one pool, and the second one, our bar, is actually the fair share of the pool. In the first one, we can say it can be for a selfish miner or an honest miner, but the second one, we show it when it chooses to mine honestly and according to the protocol. So if all miners are honest, we can say that our pool should be equal to our bar, because we have only honest miners in the network. But if we have a selfish miner, this R might be different than this one. So because we want to see if the selfish mining is profitable or not, we define a normalized gain or loss, and we define it like this. We call it G pool on so and it's a function of time. It's R T minus R bar T over 60, and 60 is for normalizing, because we have 6 blocks every hour, so that's because of that. And so this is G of pool, the G normalized gain or loss that I introduced in the previous slide, in time. So we, as I said, the profitability of selfish mining changes throughout the time. At the beginning, we start with a loss. If we have a selfish miner, for example, alpha here is 0.35, it means the selfish miner has 35% of the total revenue of the total hash power of the network, and it's lower than 0. When it's 0, it means we are equal. So it means our bar is equal to R. So it's not gaining anything and not losing anything. But when it's lower than this 0 line, it means the selfish pool starts with losing some parts of its revenue, and after a while it reaches to a point that we call break-even point. So it breaks even, and in this point it's not losing or gaining anything from doing the selfish mining, and after that it starts to grow and converge to a value, to a final value around maybe 2. So we can see at the beginning the Craig-Wright's analysis is correct and selfish mining is not profitable, but after a while selfish mining is becoming profitable. So what is our proposed method? So a good difficulty adjustment algorithm should have some characteristics. First, it should be resistant to selfish mining, because this is the reason that we are trying to come up with this idea and come up with an alternative difficulty adjustment algorithm. It should be resistant to selfish mining and ideally other types of attacks based on the difficulty manipulation. Second, it should lead to an almost constant block generation. We need this block generation to be as constant as possible, around 10 minutes that we want in the Bitcoin network. Third one is it should be able to maintain a scalability of the network. We need difficulty adjustment for the scalability. This second and third characteristic are somehow actually the first and the third characteristic are somehow in contact with each other. It means when we want to be resistant to selfish mining, we cannot maintain perfect scalability. I will talk about it later. And our fourth property is that it should be easy to understand, implement, and calculate. And the other one is it should be independently computable by peers. We don't want the peers to be communicating with each other just to calculate the difficulty. So this is the Bitcoin's default difficulty adjustment algorithm. For doing so, they multiply this value by the difficulty of the previous period. So 2016 blocks times 600 seconds over the time difference between the first block in this 2016 period and the last block in this 2016 period. So actually here we have the expected length of the period, which is 2016 times 600 seconds, and here we have the actual length of that period. So we divide the expected length over the actual length of the period and multiply it by the difficulty of the previous period to get to the difficulty of the next period. But in our proposed method, which is Zeno's, in our first proposed method, which is Zeno's, we call it Zeno's. I will tell you why. This is we have again this formula, but we call this En-1, which is expected difficulty of the previous period. And for getting to the difficulty of the next period, we add half of this value, half of the expected one, with half of the actual difficulty of the previous period, which is used in the network. So because we do this half by half, so it's like similar to the Zeno's dichotomy paradox, in which you go to the halfway point to your goal in every step. This is what we are doing here. We are going halfway through our goal, not going all the way through our goal, which is the end here. And we have also two other proposed methods, which is one of them is Zeno's max, and it's very similar to the previous one, but instead of setting dn to 1 over n En-1 plus this one, so we choose the maximum value between En-1 and this value. And also we have another one which is Zeno's parametric DAA. Also again we have another parameter called tau, and in this one we have 1 minus tau times En-1 plus tau times Dn-1. So here if we have tau as 0.5, it should be exactly like the Zeno's. So we can say that Zeno's is a special case for the Zeno's parametric when tau is 0.5. So evaluation and results. Let's talk about the results that we have here. This is one of the simulation results that we have for this one, and you can say the green line shows the original algorithm, original difficulty adjustment algorithm, and the red line is our new algorithm, Zeno's algorithm. You can see, as you can see here, for example, when we have this alpha equal to 0.4, in the original algorithm, the break-even point is somewhere around 700 or 800 hours. But in our new algorithm, we extend this waiting period for the selfish miners because we want to discourage them to performing this attack. As you can see, we extended this time to somewhere around 2,000 hours, which is way more than like 700 hours that was before in the original algorithm. So our goal was to extend this period, so we discourage the selfish miners to like try this selfish mining. And this is in another so we have another alpha here. Alpha is here equal to 0.35, and you can see in the original algorithm this break-even point was somewhere around 2,500 hours, but in our new algorithm, it is not even close at the end, which is 3,500 hours. It's not even close to the zero line. So it means even with 34% of the computational power of the network or hash power of the network, is not even close to the this break-even point. So again, we extended this break-even point further in time. And also for the when you take a look at the difficulty, so the dotted black line shows the original algorithm. It goes in one step toward the goal, but our new algorithm goes in steps. So we go halfway through our goal, and then again halfway through our goal, and then again halfway, until we reach to the final value of the difficulty. This figure shows the difficulty. The right side figure shows the difficulty for 0.35 for alpha, and as you can see, as I said in the previous slide, it goes in multiple steps. And also in the right side, you can see the block generation time, average block generation time. So at the start, we don't have any selfish mining, and here the selfish mining start to perform the mining. So after that, this average block generation time goes up to a value more than what we want, or our desired value. And as I said, the default difficulty adjustment algorithm put it at the desired rate very quickly in one step, but our Zeno DAA does this in multiple steps. As you can see here, like in steps, very much like the left-hand side, does this in multiple steps. So our Zeno's difficulty adjustment algorithm, as I told you, it can delay this break-even point even further in time, which hopefully discourage selfish mining and similar attacks. Although the block generation rate of Zeno's DAA is not ideal, it's a little, as you can see, more than 10 minutes. It can be acceptable. It can maintain the scalability of the network. It's a little bit slower. As you can see here, it's a little bit slower, like here, but it can maintain, and it is very easy to understand, implement, and calculate, because it doesn't need any. It's just a very simple formula to use on the top of the original algorithm, and then it doesn't need any more information besides what we have, what the peers already have in the network. For the Zeno's Max, we have 4 different scenarios. The first one starts with honest miner, and then another miner joins. We need these joins to we need like another miner join the network to see the effect of our difficulty adjustment algorithm on increasing the difficulty. Until now, we just talked about decreasing the difficulty. So for the second scenario, it starts with an honest and a selfish miner joins. For the third one, we start with a selfish mining and an honest miner joins. And for the fourth one, we start with a selfish miner and another selfish miner joins the network. This is the result for Zeno's Max on the first scenario. As you can see here, Zeno's DAA goes in different steps through the goal, but the default algorithm goes in one step. Zeno's Max, in increasing the difficulty, Zeno's Max acts exactly similar to the default algorithm, because it chooses the maximum value. So the maximum value here is the default value, and so it goes in one step to the goal. And here also you can see on the block generation rate, it goes in one step up to the desired value, but Zeno's goes in multiple steps. This is for the first scenario. This is for the second scenario. Again, it's very similar to the previous one, only the length of the step is like a little bit shorter. The Zeno's Max in increasing the difficulty acts very much like the default algorithm. And this is the results for the third scenario. As you can see here, we have both decreasing the difficulty and increasing the difficulty here because we start with a selfish miner, and here because we add another honest miner to the network. In decreasing the difficulty, as you can see, Zeno's DAA acts very much like the Zeno's max DAA. They're identical, but the default difficulty adjustment goes in one step. But in increasing the difficulty, as you can see, Zeno's max acts again very much like the default difficulty adjustment algorithm, and Zeno's DAA goes in multiple steps. So we can argue that in Zeno's max has a better block generation rate in when we want to increase the difficulty. So here we have a better block generation time, or average block generation time, in this scenario. And again, this is the fourth scenario, which is very similar to the previous one. In decreasing the difficulty, the Zeno's max acts like the Zeno's, and for increasing the difficulty, it acts like default DA. And we have another proposed method, which is Zeno's parametric. We have different parameters for different values for the parameter tau. We have 0, 25, 0.25, 0.5, 0.7, and 0.9. When we have 0.0 for the value of tau, it means it's actually exactly like the default difficulty adjustment, Bitcoin's default difficulty adjustment. When we have 0.5, it's exactly like the Zeno's, and we can have different values in between, and even more than 0.5. So as you can see, with increasing this value, the parameter tau, we actually put this break-even point further and further in time, and even in this parameter, which is 0.9, in this value, we don't get to the zero line in like more than 4,000 hours. So by increasing the value of tau, we can put this point further and further in time. However, as you can see in this in this figure, when we increase the value of tau, the block generation rate would be very slow. It's very slow to reaching the desired value that we want. So there is a trade-off between the block generation time that we want to get, which is 10 minutes, and putting this break-even point further and further in time. And as you can see here, this is the difficulty for different value of tau. As you can see, the green line here is like Zeno's DAA, which goes in halfway steps. Also, we have 25, which goes like 3/4 of the total step, and we can have different steps for like different step lengths for these different types of values. So when a blockchain designer wants to choose a value for their own like blockchain, they can see if they can tolerate more block generation rate like this one, and if they can choose a higher value for tau, and if they cannot, they might need to choose a like lower value for tau. So in conclusion, as I said, the profitability of selfish mining will change throughout the time, and so using Zeno's DAA, we can extend this waiting time for selfish mining to become profitable. So this will discourage the miners from performing this attack or performing selfish mining. Zeno's max, which is one of our proposed methods, improves Zeno's DAA by making the difficulty more responsive to lower block generation time. And also, Zeno's parametric can be fine-tuned by blockchain designer to better suit the requirements of their blockchain. Thank you.